Thank you so much for the introduction and for the opportunity to speak here today. Looks like, is everything set up? Great, it's just beeping at me. So anyway, thank you so much. It's been a real pleasure so far to see all the wonderful work being done, to chat with all of you. This talk will be focused on basically workflows in computational catalysis, as well as some challenges associated with them and large-scale databases. Some of these points have been discussed earlier, and we'll touch on a little bit more of those details now. So to begin, for the various databases that we have, we've heard about Catalysis Hub, we've heard a little bit about Open Catalyst Project, the Materials Project. We have millions of materials and many, many more DFT calculations that have resulted in effectively a gold mine for AI, which we have seen, and occasionally some landmines as well. And we heard some discussions about that, and I'll touch on some of those points. Of course, there's many other databases you may use other than those listed here. But if we take a look at something like the Materials Project, at least at the time I took this snapshot, about 150,000 or so materials, right? We have many more calculations. And one of the things that I was particularly interested in when I was working with the Materials Project team before I started at Princeton was how do we potentially leverage this wonderful electronic structure data that exists on the Materials Project for applications in catalysis. And this is something that's been maybe a little bit less explored than some other aspects of the Materials Project, like stability or band gaps. But how do we leverage things like the density of states? We know that, of course, the electronic behavior of materials is really important for the reactivity. And so I'll just show one very small highlight here, it's a proof of concept, and then touch on some of the workflows behind all of this. So if we want to take a look at a unique electronic character, there are many ways in which you might tackle this. One example of several that I thought about was looking at some of the prior experimental literature on what are called single atom alloys. So on the left-hand side is kind of a cartoon schematic of a representative single atom alloy where you have a host metal that's silver, you have these dopant metal species that are in orange, the copper species, and a relatively low fraction on the surface. And from prior experiments, as well as prior theory from several folks, what is predicted and shown to exist for at least this material is that you have for the copper 3D orbitals, if you take a look at the density of states here, so the 3D projected density of states, you have this very narrow D band for those copper species on the surface. And this is very different than the broad density of states that you might expect for perhaps a typical metal. It's very narrow, more reminiscent of something like a molecule, for instance. And what I want to do is first see, can we see if that data exists in analogy on the Materials Project? And the answer is yes. So the Materials Project doesn't have these highly dilute single atom alloys, but it does have somewhat fictitious alloy systems or intermetallic systems, if you will, where this material can't necessarily be made, but if we take this particular structure from the Materials Project and take a look at its density of states, what we see is that the silver is shown in gray here, and the copper density of states is shown in the orange, and it has pretty much the same density of states as that's shown for the more dilute case on the left-hand side. What this suggests is, right, we can leverage the Materials Project dataset to find other kinds of materials that exhibit this unique electronic character, and that's exactly what we did. We took the dataset of about 80,000 computed density of states on the Materials Project, but 25,000 of those are intermetallics and alloys. And then we can filter down through whatever metrics you like. In my case, I was looking at metallic structures. I didn't want to deal with lanthanides and actinides, and didn't want to deal with materials that were highly thermodynamically unstable. And regardless of how you slice it, there's several hundred of these materials that exhibit this very narrow or free atom-like electronic character on some metals in these alloy or intermetallic systems. And so, for instance, what we might find is that this nickel platinum compound would not pass our filter. There's nothing particularly exotic about the electronic structure, at least to me. Whereas this gold and nickel system would have this free atom-like character on the nickel. And we did this many times over, right? We have several hundred of these candidates, and we can take a look at absorption energies and even potentially some barriers. And just to kind of cut to the chase of what we saw, and you can check out our work if you're interested in more details, if we take a look at the prototypical example of CO absorbing on the surface, generally speaking, these intermetallics with this free atom-like character tend to bind CO much more weakly than the materials that do not have this free atom-like character. Now, the focus of this session is really on software, So in thinking about the calculations that I had run previously and the kinds of insights one might want to get from starting from the materials project and doing some sort of high throughput workflow, there are a lot of challenges that arise. I think a similar flaw was brought up a little bit earlier, which was quite nice and perhaps a little bit too small to see. But if we want to focus on one material, right, we might take the bulk structure, we might do a relaxation, we might carve a whole bunch of different surfaces. Some of those might be relatively low lying in energy, so maybe we wish to consider several of those surfaces. We wish to have some adsorbates that we put on those surfaces in many different positions, right? And what started out as one material nominally has now become many hundreds of calculations. And the challenges here from a workflow and software perspective is that we have this complex job connectivity, right? We have these dynamic jobs that are ill-defined. This workflow or this directed acyclic graph of jobs is ill-defined until we start running those calculations. If one of those jobs fails, you don't want the whole workflow to fail. You need to effectively monitor many of these calculations so that if some of them fail, you can relaunch them. You need to be able to make adjustments on the fly. You need, in general, if you're studying thousands of materials, we have diverse materials that have also diverse material challenges. So my perspective on this case is that it's very helpful, especially when working with graduate students and postdocs who don't necessarily have a background in programming, to try to separate as much as possible the logic for the scientific side of things from that of dispatching and monitoring these calculations. So on the left-hand side, I have the workflow libraries. These are where I want to run a reaction energy. I want to be able to run an NEB calculation. And on the right-hand side, we have the workflow system through the workflow engine. I want to dispatch the calculations. I want to monitor those calculations. We want to keep those, at least in my opinion, relatively separate. To date, there's, on these workflow system side of things, about 300 or so of these tools that are developed, and I keep adding to this public list when I find new ones. And that's not to say that there's obsolete tools here. There certainly are, but I think in general, there's many wonderful tools amongst these 300, and the specific tool there that might be best for you might be different for someone else in the room, right? We have different computing needs. Some folks in industry, some folks doing cloud computing, some folks doing HPC in an academic setting. So what I want to emphasize is that I'm not reinventing the wheel here. I'm not going to make the 301st or the 351st, but rather try to build upon these resources. And this XKCD comic kind of summarizes that, right? There's 14 competing standards. 14 will make one universal standard. Right now you have 15 competing standards. So in this case, right, I want to take advantage of these existing domain agnostic workflow systems while keeping it separate from the domain science itself. And so one way in which I've been working on doing this is through the development of a code, which I call QUAC for short, or the Quantum Accelerator is the full name. And this is mainly for doing high throughput quantum chemical calculations, but also we have binding calculations in there. We have more recently the machine learned force fields in there as well. So expanding to the broader array of tools one might consider for computational catalysis. Really trying to emphasize these reproducible and modular workflows that if someone is an expert in one type of calculation, you can share that publicly with another individual, where you can import these recipes straight out of the box and, of course, change settings on the fly if you wish. But if you wish to just run it as is, that works as well. So doing the kind of bulk calculation, slab calculation, absorption, maybe even some NEB calculations might be just one or two individual function calls, such that all the results at the end can also be shared quite easily on resources like the materials project. So Quack, as well as many other tools, but specifically this tool that I've developed, is built on a lot of these community resources that already exist. And that was by design, so that if you learn how to use atomic simulation environment, which many of you may have used, then it should be fairly natural to use a tool like Quack to run your calculations. So the atomic simulation environment has wonderful interfaces to a variety of different platforms, some of which I'll show in the following slide. I now help in my spare time to co-maintain ASE, but there's always more needs. So if other individuals want to help out, please chat with me, because it's a wonderful tool, but kind of we don't have enough resources to maintain to the degree we'd like. So definitely chat with me. But we then have interfaces to tools like Custodian, which Shui Ping has helped maintain and build from the ground up, and others have contributed to, where we have automated error correction. So when calculations fail, they'll automatically correct. Analysis tools also from Shui Ping, so thank you again, with tools like PyMatGen. But really what I want to emphasize here is that you have your choice of workflow manager. So if you want to use tools like those that are used on the materials project, which would be tools like Fireworks, or more recently tools like JobFlow, you can do that. If those tools don't mesh well with your kind of setup, perhaps you're not able to run a Mongo database, then you can try some of these other tools as well that maybe are better suited for one task or another, and even some tools that have interfaces to cloud computing resources as well. Of course, with these kinds of tools, if you wish, you could either just not use a workflow engine and run the calculations as is, or you can have increased observability with some of these workflow tools if you would like. So this is an example of one of those tools called Prefect, where you can, of course, monitor graphically how these calculations are running and make adjustments on the fly. And I'd like to thank Zach Ulysses as well for helping with some of the integrations here with this and other tools as well. Interoperability, I think, is really key. So it's not just enough to have just one vast set of workflows, because now we're thinking about, with computational catalysis, these machine learning workflows. We have periodic DFT calculations. We have cluster calculations on some of those individual portions around the active site in some of these periodic materials. And in this case, Quack interfaces with a whole wide range of different DFT and type binding and machine learning codes. And I encourage you to add more through just adding a new ASE calculator. I don't want to really make this sound like an advertisement, though. What I want to emphasize is that there's a lot of different tools out there. They all are doing wonderful things with various degrees of strengths and perhaps weaknesses, including for Quack, as well as other tools. So NAIDA was started, I believe, from Boris Kaczynski and others, and now it's taken off to be a wonderful effort on kind of the workflow management side of things. And there's now many individual sub kind of repos for computational catalysis. Daniel is, I believe, on my left, and has done absolutely wonderful work on a package called MKite for more broadly just materials in general, and then also a new software package that is being used on the materials project as well. It's called Atomate 2. So really what I want to emphasize is that if you're not using some of these workflow tools, certainly check them out and see if they might be of interest to you. Now, I want to take the remainder of this time to kind of show this in action and highlight a couple of caveats and challenges as we think towards maybe some of the discussions tomorrow about what are some limitations with these large-scale databases when we run them in high throughput. So the first is I used an earlier version of Quack, before it was called Quack, for making something called the Quantum MOF database, or the QMOF database. This is a database of DFT computed properties for about 20,000 or so metal organic frameworks and coordination polymers as well, which are these non-porous analogs of metal organic frameworks. We have geometries, we have energies, we have bond orders, we have partial charges, density of states, magnetic moments, and band gaps. You know, the list goes on, and you can certainly download it if you'd like. And I want to focus on band gaps. And so I've just pulled a picture here from some of Joey Montoya's older work, as well as others. So a little surprise face, but yes, it's coming back to haunt you. And here we just have a nice picture just to show the importance of the electronic structure for, in this case, for photocatalysis. This is not for MOFs, but I just thought the picture was nice to show that, yes, you might, if you were doing some sort of screening, start with some PVE band gaps, and then use that as a first pass filter, and maybe do some other properties like aqueous stability, and ultimately then have hybrid quality band gaps, and maybe even the band edges, which is what's really important for things like photocatalysis. So if we take a look at the band gap data on the materials on the QMOF database, which is also now on the materials project, what we have are 4 different levels of theory that I'm showing. On the left-hand side, we have PVE quality data, so the GGA functional. We have a meta GGA functional called HLE17, which is supposed to be meant for improved band gaps from Don Trular's group. On the right-hand side, we have 2 hybrid functionals, one with 10% Hartree-Fock exchange and one with 25% Hartree-Fock exchange. This is that HSC06 functional that maybe you've heard or used before, and just varying the degree of Hartree-Fock exchange. Now, many of us know that these PVE functionals, they tend to underpredict band gaps. That's been mentioned before. But it's not just that they underpredict band gaps. If that were the case, right, you'd have this somewhat systematic offset in this violin plot, or this box plot of all of the data here, about 10,000 data points. But that's not what you see. Instead, what you see is that when we go from PVE on the left-hand side, without any Hartree-Fock exchange, to something like HSC06, on the right-hand side, you have a qualitative change in the distribution of the data. And the question is, well, why is that the case? And what are some of the challenges there we might need to think about? On the right-hand side here, I have a plot highlighting the same data, but split 2 ways. We have the data for closed shell materials, so these without any magnetic character, and those with open shell character, meaning that, yeah, they have some degree of spin associated with them. And that explains pretty much the bulk of what you're seeing. In orange are those magnetic materials, and for the PVE functional, there's not really an overlap between those 2 data sets, or in other words, PVE predicts most of those magnetic materials to be perhaps metallic or semiconducting. Whereas if you take the HSEO6 functional, the two distributions between the magnetic and non-magnetic materials are largely overlapping. So this is potentially a cautionary tale for doing screening, at least for this class of materials, not all materials, but potentially for this class of materials, these metal organic frameworks, without thinking about spin and the effects of spin. With this data, we can also do things like train machine learning models to correct for some of those deficiencies. So if we have a large amount of PBE data and maybe a smaller amount of HLE17 data and a really small amount of HSEO6 data, you can do multi-fidelity learning. In this case, we were using the MagNet model for the multi-fidelity version of that, where you don't really need a whole lot of the hybrid quality data to get good regression going on with pretty much any functional of choice that we have here. So on the y-axis, we have the machine learning predictions, and the x-axis, different density functionals, top left being PBE and the bottom right being HSEO6. This is, of course, on the testing data. It's relatively straightforward to learn the correlation from PBE to HSEO6, but I just want to caution you that it's not as simple as just doing a linear offset. Some other challenges to think about also within the context of spin is I was looking at materials that might be either metallic or semiconducting, because those are relatively rare in these framework materials, and stumbled upon this material, which is known from experiments to have two different spin states depending on the temperature, so it has spin crossover behavior. This structure right here has an HSEO6 predicted band gap of 1.2 eV, and this structure has a predicted band gap of 2 eV. And so if I go back and forth, right, this is a high spin structure, this is low spin. The structures are very similar, but the electronic structures are very different. And the band gaps, of course, are very different as a result. This is something where these machine learning models that we train, this is where they fail completely. You have basically this near discontinuous change in the structure, going from kind of the high spin to the low spin. If you have a crystal graph of that, it's going to look nearly identical. But you have this very, very large resulting change in the electronic structure property, which you might be trying to predict. That's something that I don't necessarily have a clear way to address here. Probably needed to train machine learning models for individual spin states, but it's something that I want to caution about as well when dealing with these large data sets. Of course, when we think about machine learned interatomic potentials more broadly, if you're trying to, let's say, study magnetic nanoparticle and trying to train energy and force data, and the spins are changing as you start navigating around the potential energy landscape and training the model on that, that might cause a lot of challenges. So these are things we need to think about. Of course, that's before you even think about oxidizing it or putting in radical species as well. And one of the last things I want to highlight here before concluding is that this spin can have a really large effect. There's something called multi-state reactivity, where if you have a reactant and a product, you might have a transition of the spin state en route to that product or at the product. And that can greatly influence either the thermodynamics or the kinetics. On the right-hand side, I'm just showing a very small snapshot of some prior work that I had done on metal organic frameworks, just showing the active site of this material this was for methane activation, so cleaving the CH bond of methane. On the left side, we have a reactant. On this right side, and just kind of cut off the rest of the potential energy diagram, we have the transition state. And depending on which spin surface you're on, the transition state is extremely different. And it actually took me many weeks to find this particular spin state, despite putting in an input that should have looked like the magnetic states of that individual transition state. And these are things we might be missing. And of course, if you're 90 kilojoules per mole off on a barrier, that's not going to be so great for the rate constants, right? So looking towards the future, a few essential next steps. The first is that I think we need to think about more higher levels of theory, and that's been brought up a couple of times before, so that we can do things like delta learning and transfer learning, multi-fidelity learning on these data sets. We don't necessarily need as much as the PBE data, but we need to start thinking about how we can generate sufficient quantities of this high quality data. We need to think more about spin, in my opinion, as well as charge, which I've not brought up, and structures, of course, far beyond the ground state for training these machine learned interatomic potentials. I'll just put one brief teaser here to say that myself, in collaboration with some colleagues, are developing in Quack some workflows for these embedding methods where you might be able to predict kind of wave function quality results, absorption energies, rather than DFT quality results. So having this electrostatic embedding and having this cluster around the active site and doing CCSD parentheses T calculations on those at a fairly reasonable cost. So those will be published soon, and you can certainly check those out if you want very high quality absorption energies. So with that, I think there's plenty of work to do, But I want to, of course, thank everyone who helped make this possible. I've put some of the names here, but there's many more than I can list. And of course, I'm happy to take any questions.
Yeah. Questions?
Yeah.
Did you find from your materials project search for narrow band materials, did brass come out?
Did
Brass, I mean, so,
brass?
yeah, brass, yeah, sorry.
Yeah, no.
And then, so you kind of have, you have copper and silver. Silver is a very low dependence.
Mm-hmm.
You kind of have that copper, kind of like those copper band, the coppers, they don't see the next copper, so overlap between silver and D, and between silver and copper these days, as you have these very narrow copper states because hybridized.
Yeah, that's a good point.
Brass is the same, so I was wondering, is there no brass? Is there no brass in the project? I mean,
So
brass is copper and zinc. It's the same thing. The zinc these days are super low in energy.
yeah, so I didn't look specifically, but if you take a look at the right-hand structure, you really don't need a large amount of interatomic distance between those to the dopant or minority atom there. So I would imagine that a case like brass would very likely have similar, but I guess it depends, of course, the particular atomic arrangement there. But I would say it's reasonably likely you don't actually need a large degree of separation to have the narrow D states on those kinds of materials. But now I'm curious, I'll certainly check it out.
I think brass is, and that's why I remember from X-ray experiments that they see very narrow states, and brass has the same effect on copper. Also, they are isolated copper atoms.
Yeah, I'll check it out. Thank you. Yeah, Brandon? Oh, sorry, I didn't mean.
When I'm looking at these really large workflows, what I'm thinking about is like anomaly detection. So there's all these times where you do these calculations and like converge to something weird. There's a type of spin state, you might not converge to steps. What are your thoughts on getting the anomaly detection to the point that you're like, okay, everything I'm calculating in this data set, it was fully converged exactly the way I hoped it's.
Yeah, that's a really good question. I found many times before when trying to find materials with unique electronic structures, the ones that come out are the ones that are just complete garbage. So metallic MOFs or other kinds of structures, 100% I found that. For these D states, I did manual inspection of those and they seem to be okay. So I haven't really spotted anything there, but I've totally spotted the situation you're talking about more broadly. I hope to have some answers to that question. I'm actively working on that. I don't have any answers to that at the moment, but I do think that there's a lot of work that can be done there with machine learning. If we maybe take real structures and artificially make them incorrect, right? Trying to create these anomaly detection algorithms that way are probably worthwhile to pursue.
Awesome, thank you.
Right, great problem. My question is regarding magnetism. So I think there are different levels of magnetism.
Yep.
There's the usual one where we just assume everything is ferromagnetic. There's the one where we still assume that there are changes in magnetic state, but we still assume being a magnetism. There's of course the most complicated one, which is non-code. How important is it that you actually capture something like non-code?
Yeah, so that's a really good question. I'm not sure, to be honest, about the non-collinear magnetism, just because I haven't run too many calculations of my own, so to really report back. But for maybe a rung below that, thinking about like anti-ferromagnetism, for sure, for something like catalysis, depending on the types of materials you're studying, if you have these like single atom catalysts in like a metal organic framework or others, that can be many tens of kilojoules per mole different on something like a barrier. So it's not just, I want to initialize high spin, I want to initialize low spin, and I can move on with my life. It really is about finding the spin state there. And these are really, really big challenges to think about for sure.
Yeah. So, yeah, thank you. Thanks.